Okay, so you can open the King drawer, you can start a new page, and then the interface is very user-friendly. It's just that it's like any, it's like using Word or Excel or PowerPoint. It's that whatever you're using has to be the thing that's highlighted. So like if you want to make something bold on Word, you know that the bold icon has to be highlighted, or if you want to underline something, you have to underline the bold. So it's the same with this. If you click on something, so I want to draw a line structure, I got to click on the line that I want to draw, and then I can start drawing the lines like that. So that's quite cool. And then if I want to, I can also add extra atoms. So if I want to add an oxygen, I click on the oxygen. You see the highlighted oxygen is highlighted. And then I can add like an OH group, for example. Cool. And then you have options at the bottom, in the bottom right and left hand corner. And what I can also do now is I can actually name this thing. So we just give it a few minutes, seconds, hours. Let's see how long it takes. And there we go. So hex for 6, 3 for the position of the alcohol, and then OL for the OH group. Cool. Any questions?
I'm good.
You good? Okay, so then what I can do now is I can go to the top right-hand corner of my page. There's the 3 little dots. So sort of midway between the 2 apps, I can click on the 3 dots and I can save that as a JPEG file. So I can save that there. And then once it's saved, I can import it. Like if you save it on your desktop, for example, if you're using a home computer, you can import it in Word or PowerPoint or Excel or whatever you want. So it's there. So then you just go to library, recently added, and then you add that. And then you can obviously position it anywhere you want. Cool. And then you can crop it as well. You can actually change the size, crop, and get rid of that thing at the bottom. Okay, so hexan 3-ol. Now what we can do is we can do all the other structures. We can do the molecular structure, we can do this structural formula, and we can, well, we've got the name already. So we can count the number of atoms. It's 6 carbon atoms, so it's C6. Hydrogens should be double plus 2, which is 14. And then I have the oxygen as well. But would you agree with me that the molecular formula is useless because I can't tell where that oxygen actually is?
Yes.
Yeah, cool. But then what I can do is I can write out the structural formula. So I can write out the CH3, and I can write out the CH2. I've got another CH2. Then I've got the CH in the middle. And remember, always do the H's before the OH's so that you don't get confused, because if I write that, you can see that that's the OH there. Then I have another CH2, and then I have the CH3. Okay, so I can see I'm going to run out a lot of space here. So let's make you a little bit bigger. There we go. So that looks horrible. So I'll work on my handwriting. But what I want to do is I just want you to remind you that you've got it, when you play around with these things, remind yourselves what you're looking at. So that carbon is that carbon. This carbon here is that carbon there. This carbon here is that carbon there. That carbon there is the most important one because it's the one that has the oxygen on it. And then that carbon there is that carbon, and that carbon is the last one. So that's what you've got to do. You've got to like play around with these things and make sure that you understand that everything in the skeletal formula is also represented inside the structural formula. Cool.
Sir?
Hello.
So even though it's a hexagonal 3, we
Correct.
don't have to write CHOH as the third carbon. We can leave it as it appears.
Yes. Correct. So that's exactly today's topic. That's exactly today's lesson. So what we're going to do now is we're going to go back to King draw. And what I'm going to show you is that you can optimize the structure to give it in its lowest number configuration. Cool. So now look on the left-hand side. I'm back on the King draw. Cool. So what I'm going to do is I'm going to lasso the molecule that I want. And what I'm going to do is there's a little button that looks like a magic button in the bottom left-hand corner. You'll see when I click on it now, it'll get highlighted. There we go. And in that case, can you see it puts it on the third carbon?
Yeah.
But it's also flipped it upside down. Cool. So what I'm going to do is I'm going to move that over there. I'm going to copy it, and then I'm going to paste it. I'll paste it underneath. I'm going to highlight the bottom one again. And then what I'm going to do is I'm going to flip it on its horizontal axis like that. There we go. And then what I'm going to do is I'm going to save that as an image, JPEG. And then save. And then I'm going to import it on my drawing side. One, oopsie. That one there. Add. And what you're saying is absolutely correct, because those are all three the same representation of the same molecule. They're not different molecules. But would you, what you said, Kamas, would you agree with me that this one over here is the sort of ideal structure?
Yeah.
Because it has the hydrogen on, it has the OH on the third carbon. So if we were going to count, we can count from here. We can say that's 1, that's 2, that's 3, that's 4, that's 5, that's 6. If we were going to count here, that's 1, that's 2, that's 3, that's 4, that's 5, and that's 6. And we could say that that is not ideal. They're not wrong. There's nothing wrong with writing it that way. There's absolutely nothing wrong with displaying it in any way you want. However, in order to name it, it would be easier to read it left to right, because as English-speaking people, we read left to right. Cool. But what's the most important thing in not reading left to right? What's the sort of underlying principle in terms of giving it numbers?
On which carbon it is on.
Correct. And then how do we assign them a number? On what basis? What's our sort of principle? Like, in other words, we had an option. I'll show you now, I'll highlight it for you. We had an option to put it on either 3 or 4.
Isn't it that we count from the lowest possible thingy?
Correct. So we give them the lowest number, lowest number carbon. Yeah, so we give it the lowest number carbon. That's correct. So that's basically the idea. So all the structures are correct. There's nothing wrong with drawing it either one of those 3 ways. However, in terms of counting, it would be ideal to have it on the left-hand side, because that's how we read. But would you agree with me if I had to rewrite the structural formula would also change? Yeah, because the OH group would shift onto the third carbon. The OH group for the ideal one would not be on the 4th carbon, it would be on the 3rd carbon. But it would be identical in terms of it's the same molecule. It's not a different molecule.
They don't mean.
Pardon?
Nothing. I was about to say something stupid.
No problem. So this is basically the lesson topic. Sorry, I didn't tell you in the beginning, but if you look at the top right-hand corner, the heading of the topic is the same molecule drawn differently. So it's basically saying we're not learning anything new about the molecule, or like any different types of the molecule. It's the same molecule with a different representation. Cool. And then what you can do is you can go back to your king draw, you can clear everything, and then you can start over again. Okay, so what I'm going to draw, you don't have to be able to name anything longer than 6, but what I'm going to draw is a really ugly looking structure, and then we're going to optimize it. And I've seen questions like this before in exams where they make you think that it's a completely different molecule, in the meantime, it's actually the same molecule drawn in a different way. Also, they do something like this. And then they'll take it at an angle and they'll move it around like this. And they'll go like this. And then they'll add maybe like a chlorine atom, let's say there, a chlorine atom. Cool. And you'll look at that molecule and it'll look horrible. And you'll think, oh goodness, this thing can have like 1,000 different representations. But what happens when you optimize it? You can actually get those bonds to form the zigzag patterns. So you can take it, and if you optimize it, you've actually essentially basically drawn that molecule over there. And it's not that obvious. What you really have to do is you have to count the number of carbons and ask yourself, is the chlorine in the same position on both molecules? Oopsie, how do I close that? Oh, I have to use my fingers. Okay, so save that. Oopsie, save as JPEG. And over here, we import. Oopsie, which one is it? Oh, I have to press save first. Oops. That one. Oh, go in. Add. Cool. So I'm going to take you back a little bit. Think about bonding. What is unique about a single carbon bond? Or what is unique about any single bond before you add the double bond?
The single bond is unsaturated, maybe?
That's correct.
Saturated.
Correct. It's unsaturated, so it's unsaturated. Correct. I don't want to give you the word because I want you to think about it. Think about when we talked about overlap of orbitals. What type of orbital overlap do you get? Does anyone remember what's the type of overlap that we get in single bonds? They're two Greek letters, and one of them sounds like something that you eat.
Jesus Christ.
Pi,
Oh,
sigma, and pi.
Sigma and pi, correct, sigma and pi. Cool. So these are all sigma bonds. And the thing with sigma bonds is that they're free to rotate. So there's rotation. So the important thing here is that we can rotate the molecule. And by rotating the bond, I don't mean we're creating a brand new molecule. What I'm saying is that we're free to rotate that thing 360 degrees around its axis, meaning that if you look at these bonds and the way that they're drawn, that one, for example, that one, it's the same bond, it's just been rotated. Where's that one? Let's go orange. That bond is the same as that bond. Oh, whoopsie, whoa, no, that's not that one. That's not that one. Whoa, it's the other end. Okay, let's choose one from the other side rather. Chlorine. Wait, let's choose 2 away from the carbon, 2 away from the carbon. Let's draw you in red. Yeah, that bond there is that bond there. And what do you know about the ideal angle for a tetrahedral? What value do we
Is it the
assign
angle
to?
itself?
Correct, the angle itself. It has a very specific assigned angle, a very specific assigned value. So it's tetrahedral. I'll give you that. It's tetrahedral. And who can remember the bond angle? So it's a very specific number.
109.5.
That's the one, correct, 109.5. In other words, that bond angle between those 2 carbon atoms there, or 3 carbon atoms with the one in the middle, that angle there is going to be 109.5. And can you see that the zigzag structure kind of tells you that, because 109.5 is approximately 1/3 of a circle. So if you look at that angle there, would you agree with me that it's approximately 1/3 of a circle?
Yep.
Yeah, so it's if you thought about a circle like this, and you divided it into 3 sections, oh, that's not a good way to divide into 3 sections. If you divide it into 3 sections, you've approximately divided into 120 or 109.5 or whatever. So in other words, those bond angles is what gives it that zigzag structure, if that makes sense. Everyone happy with that?
Yes, sir.
Yep. So basically
Yes,
what we're
sir.
saying is that it doesn't matter where you draw it. It doesn't matter where it's represented. That bond angle there is always 109.5 degrees. So it's 109.5 degrees in all the molecules. The only thing that's changed is we've rotated around that angle. We've rotated around that bond, but we haven't changed the angle. You guys were going to play with the modeling kits today, the actual physical modeling kits. I had them out and everything, like they're literally ready for you to use them. So that's unfortunate. So you can't do that. But what you can do is you can visualize the 3D structure on the Chem mod side. You can actually take the molecules and you can rotate them and play around with 3D structures. So you can do that, and you can actually see the bonds. Yeah, there you go. If you position it like, oh, it's difficult to, there we go. There you can kind of see the backbone, the 109.5 degrees between the carbon atoms. Cool. Guys, I know I'm making notes to give you notes. I forgot to tell you this in the beginning because I was in such a rush to get started, but it's also a good idea to be taking notes simultaneously in any case. So for future reference, just make sure you have your notebook with you so that you can take notes while we're talking. So whatever I'm copying down, you're basically copying down simultaneously. And it's got nothing to do with the fact that it's the notes are there, the notes are not there. It's a brain, hand, eye process so that you're not just watching and listening, you're actually using your hands and you're creating a third connection in your brain so that the material sticks a bit better. So it's hand, eye, brain, ear. It's all your senses being used simultaneously.
So,
You know,
what if the molecule had a double bond?
we're going to talk about double bonds today. Double bonds would have a pi bond and you would be limited by your rotation. And in that case, you would get isomers. So what we've talked about today are not isomers. They're exactly the same molecule. They've just been rotated to a different, same angle. We've just rotated around the bond. But you'll see with the double bond that because the atoms are fixed in position, we can't get rotation. So you end up with 2 different molecules in that case, like completely different. That's tomorrow's lesson, if you don't mind waiting.
Sure.
Cool. If you really want to, you can call me later and we can talk about it today if you want, or you can read the textbook. But yeah, isomers are very fascinating.
What do you mean by rotation again? I don't like. What are you saying?
It's difficult. It's difficult to see. So what I'm going to do quickly, if you give me 2 seconds, I'm going to get the physical model kit and then I'll show you. So just give me 2 seconds.
What's up, guys?
Hey. I wanted to.
Oh, Nico's sleepy voice.
Oh,
Oh, Nico's sleepy voice. Hit different.
I was wondering, do carbon bonds have 109.5 degree angles?
No, I don't think so. It's just the carbon that's bonded to 4 things that
Oh, okay.
that
But
don't
wait, it
have
wasn't-
lone pairs of electrons. Like, so a tetrahedral will be carbon bonded to 4 hydrogens because they don't have
I know
double bonds,
that.
so it's
Yeah,
equal
I
to-
know that, but like, why was it in that case? Because there wasn't 4 molecules.
But
I'm
isn't
going
it
to
carbon?
I'm going to share. Oh, sorry. Were you guys talking?
That's
Yeah,
okay.
no, he was asking about why that's considered a tetrahedral.
Okay. I'm going to show you now. So I'm going to put on my video now. So you'll see me. Hopefully not me too much. Let me put me as pin. There we go. Perfect. There we go. Okay. So there's the molecule. And I'm going to put the 2 red ones at the top now. So I'm not sophisticated enough yet to draw and have the video on at the same time. But what I'm going to show you is this. And then I'm going to draw it for you. And I'm going to explain to you that we can make the same molecule look differently by rotating the bond. Cool. So would you agree with me that the two colorful ones, as opposed to the white ones at the top, the red and the green?
Yep.
Yep. Now,
Yes,
if I, yep. And if I turn it to the side like that, would you agree with me that between the purple and the red, that's the 109.5 degrees? That's the bond angle I'm talking about.
Yes, sir.
Cool. So that's the bond angle. So now look what I can do, because it's a sigma bond, this one in the middle here, that's a sigma bond. In fact, they're all sigma bonds. I can actually rotate the molecule. So the beauty of the modeling kit, the nice thing with the modeling kit, what makes it so excellent as a teaching aid is that whatever you can do on the model, the molecule can do itself in real life. So it's not realistic because it's a model, obviously, but we have theories to suggest that this model is accurate. So it's been suggested that these bonds can rotate and you can form different rotational. They are technically a form of isomers. They're called rotational isomers, but we don't really consider them isomers because it's the same molecule.
So,
Yeah, like I haven't changed the chemical properties of this molecule. It's exactly the same molecule. I've just rotated the bond. Cool.
Mhm.
yes, sir.
Good, good. Okay, so now I'll draw it for you on the iPad and I'll show you what I mean by that. A simple one, nothing too complicated, just a very simple 2-atom molecule. You unlock. Do I have to, I have to mirror the screen every time. I'll figure this out eventually. This is day one for me too, so just forgive me for a bit. What I'll do is after the note, I'll take a picture of the actual model and I'll put the picture of the model in the note. So I'll do that as well. I'll put them all together. Here we go. Okay, so we want a two carbon molecule. So literally all we need is a line. Literally, whoopsie. Where's undo? Literally all we need is line. And what we're going to do is we're just going to add 2 extra atoms. We're going to add chlorine and let's say oxygen. There we go. So that's 2 carbon atoms in the middle, and then there's oxygen and hydrogen. And what I can do is I can copy that molecule. Then I can paste it. Whoopsie, copy and paste. There we go. I can take the same molecule now. Whoopsie. Oh, no, stop pasting. Undo. Stop pasting. Don't do that. I can get rid of that oxygen. I can get rid of that bond. And I can do that. I can do that. And I can put the OH over there. But that's the same molecule. So there's absolutely nothing different about these 2 molecules. All I've done is I've rotated that bond in the middle. So I'll copy it to the other screen, then I'll show you. JPEG, save, media, add you, add, put you in the corner, crop. Sorry, I think out loud. I'll stop that next time. Okay, so if you were going to draw the displayed formula, you could draw the displayed formula for each one. So if you're going to draw the displayed, you could write this as carbon, carbon. You could put the OH at the top here. You could put the hydrogen at the bottom. You could put the H there. H, H, H. And if you're going to draw the displayed formula of this one, you would draw it like this. And you put the OH at the bottom, H there, H, 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 and H. But would you agree with me that it's the same molecule?
Yes.
Yeah, so all I've done is I've taken this bond over here, that bond, this carbon here, and all I've done to get from there to there is I've rotated that bond. Also, I've rotated, let's put you in, no, not black, let's put you in orange.
So where's the chlorine?
The chlorine should be there. The chlorine should be there. Let's put the chlorine. Let's keep them in the same place. Let's keep the chlorine at the bottom here. Thank you for that. Whoever's not on the Zoom would have been highly confused if you hadn't said that. Here we go. There's the chlorine. So relative to the chlorine, in the bottom molecule, they're on the same side. In the top molecule, they're on opposite sides. But all we've done here is we've rotated that bond. So all we've done is we've rotated it. And it's the same molecule. There's absolutely nothing different about those two molecules. They have the same chemical properties. They have the same melting point, same boiling point, everything. In reality, there's a preferred configuration, and nature decides what it prefers based on electrostatics. So in other words, if the oxygen and the chlorine are close to each other, what do electrons hate more than anything else in the world?
Each other.
Each other, correct. Electrons hate electrons. So the OH and the Cl, because they're such large atoms and they contain a lot of electrons, those two atoms will try to get as far away as possible if they can. So just based on that, which configuration do you think would be ideal?
Top one.
The first one, maybe?
Correct. And
The top
you got
one.
the top one. The top one would be the ideal configuration because the OH and the Cl are on opposite ends of the molecule. So when I showed you the molecule in the first time, let's see if I can do this without changing anything. Oh, I just start my video. Wait, no, don't share. Let's just start video. Start video. There we go. And then I pin the video. Am I right? What do you see bigger, the iPad or me?
The iPad.
But you can see me in the little top right-hand corner.
Yes.
Yes.
Okay, so that would be the less ideal configuration because the red and the green are together on the same side of the molecule. But if I rotated it like that, the red and the green are as far apart as possible. And that's just a rotational thing. So in other words, if the molecule's floating around, this bond is free to rotate as much as it wants. However, once it reaches that configuration, it's probably not going to want to leave that configuration. It's probably going to want to stay in that configuration.
Sorry, I missed out on
No problem,
a
no
little
problem.
bit.
So what
Is
I'm
that-
saying is that, yeah, say what you heard and then ask me the question.
Why is it that in that configuration it
Because the red atom and the green atom are high electron dense atoms. They contain a lot of electrons as opposed to hydrogen, which has very few electrons. Oxygen has about
Okay.
6, chlorine has about, I don't know, 35 or something ridiculous. And
Alright,
because of electrostatic repulsion, literally just like negatives hate negatives, they want to get as far away as possible. But if you think about it, do you remember the Boltzmann distribution? Yeah, in terms of the Boltzmann distribution, you'll probably find a small proportion of the molecules that actually exist in this configuration. So statistically, you might actually find like 5% of the molecules in this configuration, but you would probably find about 95% of them in this configuration. I'm saying if you had like a container full of these molecules.
Right. Okay.
Cool. So it's just yellow.
In the first picture, in the first drawing.
I'm gonna stop the video quickly. Just let me turn the video off and go back to the iPad. Okay, so which one?
Sir said it's the carbon that rotates.
Yes, let me just quickly get the screen sharing and then I'll see what you see. I need to figure out how to keep this permanently on. It keeps turning off. I think I must set the screen time to stay longer on. Okay, so ask the question quickly, then I'll see the picture afterwards.
Okay, sir said it's the carbon that rotates.
Correct.
But it looks like it's the OH that is rotating.
I agree with you 100%. It's not the carbon that rotates, it's the bond between the two carbon atoms that rotates. It's a pity you're not here. Yeah, it's a pity you're not here to see this because I'm going to show you now quickly. So we've got 4 minutes before the video cuts off. So I'm going to get rid of the iPad and then I'm just going to focus on this one. So
yes.
when you see this bond here, your rotation is actually coming from this bond over here. And if you see where I hold my finger, can you see that I'm actually rotating on that point?
Oh, yes.
So the
yes.
carbon atom itself is not really rotating. It's relative to this bond here that it's rotating.
I see.
Yeah, so that's rotating over there. So this angle here is 109.5. And if I rotate it down, can you see I haven't changed the angle? It's still 109.5.
Yes, sir.
Yeah, so that bond is not changing. What I'm doing is I'm rotating it relative to this atom, the one
Yes,
on
sir.
my left. So I can rotate about that bond. And the reason is because it's a sigma bond. And when there's sigma bonds, you know that they have front on overlap. There's no side on overlaps. So that bond is free to rotate into whichever
Yes, sir.
orientation it wants. Cool. Okay.
So
So
what-
guys, Yellow, talk to me.
What causes the rotation?
Nothing, absolutely nothing. They are allowed to rotate into whichever configuration they preferred. So
Oh.
if you had like a sample of molecules, let's say you had 10 of them, it's probable that you'll find maybe 1 in this configuration and about 9 in that configuration.
Oh, okay.
And if you really want to ask the question, what causes them to rotate to this configuration? It's because the red one wants to get as far away from the green one as possible.
Oh, okay.
And it's free to rotate because it's a sigma bond.
Okay.
Cool. Guys, we've got about 3 minutes, then the meeting's going to end. So before it ends, I'm going to send these notes online. But what I want you to do is I want you to keep playing with your molecules. In other words, draw your tables. Oops, you can't see that in focus. I did one yesterday of about 10 molecules. This is what you were going to get in class today. So I'm going to scan this and put this online. But what I want you to do is just keep playing with this. And then obviously revise your functional groups. Any questions?
Cool.
Okay.
We good? Awesome. Okay, I'm going to end the meeting. I'll save the video and then I'll upload everything onto Google Classroom.
Hi.
Thanks.
Bye guys, see you tomorrow. Tomorrow's meeting, don't forget, we start at 11 and we have a double lesson, so we have an hour. So 11
Yes,
to
sir.
12. We'll break it into 2 30-minute lessons.
Okay.
Cheers guys, bye.
Bye.
Bye.